in this lab 2 on projectile motion, I analyzed the motion of a thrown pickleball using both experimental and computational models with and without drag. The goal of this lab was to compare the motion of a projectile under the influence of gravity and drag using both tracker data and computational modeling. The object I used was a pickleball with a mass of 24.3 grams. I tracked its motion using tracker and simulated it in close grip. On this graph, we're comparing three trajectories. The blue dots represent the experimental data, which was collected using the tracker app. The orange points show the results from the gravity-only model, and the green points represent the gravity plus drag model, which includes air resistance through a drag force. You can see that the green curve with drag follows the experimental path much more closely than the orange one. In this experiment, we modeled the motion of a pickleball affected by gravity and air drag using fundamental physics principles. First is velocity update formula. This comes from the Newton's second law. Acceleration is defined as a change in velocity over time, so this formula lets us update velocity step by step using the net force acting on the object. Next is a position update formula. This equation updates the object position by adding its average velocity over a small time interval to its initial position. In our simulation, this formula helps track the continuous path of the ball frame by frame as it moves through space. Speaking of forces, the force of gravity. This vector points straight downward because gravity only affects the vertical direction. Finally, we have the drag force. Drag depends on the square of velocity and always acts in the opposite direction of motion. The coefficient b represents how much air resistance affects the object. Our system was a pickleball and the surroundings included earth and air. We tracked its motion using a reference object for scale and captured position data frame by frame using tracker. Here you can see the data I collected using tracker. This includes the position of the ball in both the x and y directions over time from t equals 0 to t equals 0.5 seconds. This data served as my reference to evaluate the accuracy of the computational models. From the tracker data, I calculated the initial position and velocity. For example, from the first 2 points, I used the displacement over time formula to calculate an initial velocity. Here's a closed grip code for the gravity-only model. You can see on line 63 that we set the drag coefficient b equals 0, which disables the drag force entirely. The only force acting is gravity, represented in line 79. We then use Newton's second law to calculate the acceleration and update velocity. This is a closed grip code for the gravity plus drag model. In line 63, we introduce the drag coefficient b equals 0.003, and then calculate the drag force as in line 80. This drag force acts opposite to velocity and is proportional to the square of speed, a realistic model for object moving through air. Adding this term makes the simulated motion much more closer to the real motion we recorded. Now let's compare the simulation results side by side. On the left, you see the gravity-only model. The velocity decreases linearly and the object drops very steeply. On the right, you see the gravity plus drag model. The velocity decreases more gradually, especially after the peak, and the trajectory is flatter and blurrier. This graph compares three trajectories. The blue dots represent the experimental data from the actual pickleball motion. The orange dot represents the gravity-only model, and the green dots represent the gravity plus drag model. As you can see, the gravity-only model falls much more quickly than the experimental data, which indicates that it's missing a force, namely air resistance. The gravity plus drag model aligns much more closely with the experimental trajectory, especially around the peak and descent, showing that the drag force plays an important role in slowing the object down in real-world motion. Some deviations may come from misidentifying the center of mass, rounding in tracker, or inconsistent air currents in the room affecting motion. What does it mean for an object to reach terminal velocity? Terminal velocity occurs when the net force acting on a falling object is 0. That is when the downward gravitational force is exactly balanced by the upward drag force. This results in 0 acceleration, meaning the velocity becomes constant. In our closed grip model with drag, we notice that the y velocity starts off increasing in the negative direction but gradually levels off. This flattening behavior indicates that our drag-inclusive model does indeed approach terminal velocity, especially as the object falls longer. This matches the expected physical behavior of objects in free fall through a fluid like air. In contrast, the no-drag model shows a constant acceleration, meaning terminal velocity is never reached because there is no upward force to counteract gravity. Now for the second question, to answer this, we apply a simple kinematic analysis. The time to reach the ground depends on vertical motion. If we throw upward, gravity acts against the motion first, slows the object to 0 velocity, and then brings it back down. The total vertical time is t equals 2v0y divided by z. But here's the key, the upward journey adds extra time. Even though the starting speed is the same, the object has to slow down, stop, and then fall back down. This means the total flight time in the thrown upward case is longer than in our original diagram at launch. Additionally, air drag will cause it to reach a lower max height and descend faster, further modifying the time depending on the drag coefficient.